Happy Friday, everyone. And this is the last new day of circuits material. And we've got internal resistance. So we need to remind ourselves about Kirchhoff's second law first today. So in this circuit, for example, Kirchhoff's second law tells us that the sum of the EMFs has to equal the sum of the PDs in a closed loop. So here we've only got one source of EMF, so the sum of the EMFs, that's just going to be 6 volts. And that has to equal the sum of the PDs round our closed loop. So that means that the PD across the resistor also has to be 6 volts. We can then use Ohm's law to calculate the current that we're going to get. So the current will be V over R. So the PD 6 over, right, I'm going to say 10 ohms for my resistor there, because it makes all the numbers nice. So then we're going to have 0.6 amps of current in our circuit. Okay, however, this is not actually realistic. In fact, every component has some resistance, and the cell definitely has some resistance, and we call it internal resistance. You can't actually see the resistor. You can't put a voltmeter around the resistor, but the resistance is there inside the cell. To show this, we draw our cell and then we draw a resistor, but we put this dotted box around to show that this is not a resistor I can see like that one. It's inside the cell. So that's how we draw that. Okay, so what difference does it make? Well, let's stick with 10 ohms here and an EMF of 6 volts. And a typical internal resistance for a cell would be 5 ohms. Okay, so what difference does it make? Well, first of all, we know that we've now got, instead of only 10 ohms of resistance in the circuit, we've now got 15 ohms. And so this resistor, now it's going to get only 2/3, so 10 is 2/3 of 15. So this resistor is going to get only 2/3 of the available PD. So that's 6, so is the total available, so it's going to be 4 volts only across this resistor. So in fact, it can't get the full 6 volts. And then this resistor, the resistor that doesn't really exist, the inside of the cell, that one there, that one is going to get 2 volts. So you can't do this, but just pretend that you could. Imagine if we did attach a voltmeter across the inside. This is not possible, but just for the sake of argument, if that were possible, then this would read 2 volts. Now, we've got no way to get at that 2 volts, and so it's known as the lost volts or the lost PD, because we can't get at it, we can't use it. It's being used up inside the cell. So the PD that we can get at, which is in the outside part of the circuit, that is called the terminal PD. And that's because the outside of the circuit is sort of from one terminal to the other terminal of the cell. So the PD between the terminals. Okay, so the PD across the resistor has gone down, but notice also that if we calculate the current through this resistor, 4 volts over its resistance is only 0.4 amps. So now the current through the resistor has also gone down. Okay, so you might think, well, that's nice, but how on earth do we work out, if we can't stick a voltmeter across the inside of the cell, how on earth do we work out what the lost volts is and what the resistance of the cell is? And there's a really nice practical that gives you that. Okay, so what you do is you build this circuit and you are going to vary the resistance of the variable resistor. And every setting that you put it to, you write down the PD across it and the current through it. And then you're going to plot a graph. But before we look at the graph, we look at what's going on with these numbers. So from Kirchhoff's second law, we know that the EMF of the cell has to be equal to the PD across the variable resistor, so I'm calling that V, plus the PD across, and I haven't drawn it in, let me just add it in. So there's my resistor representing the internal resistance of the cell. So the PD across that is IR, the current times its resistance. Okay, so we do a bit of rearranging. EMF minus IR equals V, and then if you compare that to Y equals MX plus C, it's a little bit jumbled up, but if we put this on the Y-axis and we put I on the X-axis, then C, the Y-intercept, will be the EMF, and M, the gradient, will be minus R, minus the internal resistance. So here is what you'll expect your graph to look like, and those values again. So the Y-intercept, this is the shape your graph will turn out, and this here will be the EMF of the cell, and then you can see that there's a negative gradient because that's equal to minus times the internal resistance. So then the internal resistance is minus times the gradient. So it's quite neat. I like this graph because it tells you something that you can't directly measure.